or accretors would be black holes or neutron stars accreting from companion stars. And they'd be accreting at pretty high levels relative to, say, the Eddington level of accretion. All right, so X-ray binaries themselves as a population have the promise of providing a lot of interesting information. Okay, so we can learn about binary populations in galaxies, we can learn about compact objects, we can learn about accretion, and all kinds of other interesting astrophysics that go along with studying compact objects in this extreme regime. The populations themselves, this is sort of looking to the future as something that could be useful, but when we're studying the populations themselves as demographics, they can sort of relay information about the galaxy. So for instance, the formation of these populations are sensitive to the history of star formation in galaxies. They're sensitive to the metallicity in galaxies from which the stars formed. And then also stellar density can have a role in the formation of these objects through dynamical interactions. And so these can be tracers of galaxy populations. Furthermore, they're also an additional population that tells us about other very interesting astrophysical populations. So gamma ray bursts, in particular, say short gamma ray bursts, the phenomena related to producing those are going to be similar to those of X-ray binaries. There are millisecond pulsar populations out there that are thought to have once been X-ray binaries, gaining angular momentum by accretion, and then gravitational wave sources. So a lot of these various populations, if you want to understand them, you have to invoke a lot of the same astrophysics in order to understand those as you do with X-ray binaries. Finally, one thing we've been learning over the last decade or so, or getting a better handle on, is that the X-ray emission from the populations themselves and potentially mechanical energy that's being put out by these populations can play a role on the galaxy. So for instance, the ionizing radiation from X-ray emitting populations can have an impact on the interstellar medium. And then also in the very early universe, there's likely to have been some heating of the intergalactic medium due to X-ray binary populations at redshifts greater than around 10 or something like that. Okay, so just to, again, sort of help with orientation here, I'm showing this image. This is an image of a Chandra image of the galaxy M83 in X-rays. Down here is the inset of that galaxy in the optical band, which you may be more used to seeing. But in any case, in this image, what you can see are a variety of different phenomena. So we have this red kind of diffuse glow throughout the galaxy. It comes from diffuse gas, which is, again, interstellar medium that's being heated by massive stars or supernova. And at the depth of this particular image, you can even see individual supernova remnants themselves in other galaxies. Okay, there's also X-ray binaries that a type of X-ray binary that we call high mass X-ray binary. And these would be those X-ray binaries that are fed by a high mass star. And in this case, you might have a black hole or neutron star here, accreting from a very massive star through either a stellar wind or through just mass transfer of material from that star to the compact object. There are other varieties of X-ray binaries. For example, low mass X-ray binaries are more likely to live kind of in the vicinity where you have older stellar populations. And so these things would form on the timescales of the evolution of the low mass companion star, which could be billions of years. And I'll talk more about these various populations throughout this talk. All right, so if we look in a cumulative sense of the X-ray spectral output of a galaxy, we can break it down into these various components. And so this is a diagram of maybe a characteristic spectrum of a galaxy that's star forming active. In red, this is this is a model, by the way. There could be sort of detailed lines coming from plasma, so a low density plasma that's very hot. So this would be hot gas, and then supernova remnants that would contribute to the overall power output. And this is usually low energy emission from the galaxy. But then as you go over to higher energies, in terms of photons, the entire galaxy's population, or the entire galaxy's emission, is dominated by these X-ray binaries. Okay, and so it'd be this variety of high mass X-ray binaries and low mass X-ray binaries. All right, so the state of sort of the, research that I do 10 years ago was such that people were interested in looking at scaling relations. So how do the formation of these various populations of X-ray binaries scale with galaxy properties? And they do this, various papers would do this in a, at various levels of detail. It was recognized, maybe 2 decades ago, that if you took a sample of star-forming active galaxies, for instance, and measured all the X-ray luminosities of those galaxies, and made a plot of the total power output of the galaxy, which is by X-ray binaries, between those two quantities, right? And this is thought to be due to the formation of these high mass X-ray binaries, where the high mass X-ray binaries themselves will not live for very long. Of course, you have a massive star companion there that will not live for very long. But the X-rays at, say, elliptical galaxies, where star formation has ceased long, long ago, billions of years ago, there's still rich populations of X-ray binaries. And these would be the low mass X-ray binaries that take a long time to form. And so then you can go and collect a sample of passive galaxies, mainly like elliptical galaxy mass. And again, you see sort of a correlation. And this is because, the larger the number of stars that you have, the larger number of low mass X-ray binaries. We could do more than this 10 years ago. And, people would then look at, say, this, and then look at how, for say, star-forming galaxies, how that luminosity function scales with star formation rate, and then for passive galaxies, how the luminosity function scales with stellar mass. And so this led to, showing that the high mass X-ray binary luminosity function is just very high luminosities, and then the low mass X-ray binary luminosity function has a steeper slope over here, not reaching as high of luminosities as the high mass X-ray binaries there, right? But one of the things that was noted, but is that if you try and scale all these, as has been done in this diagram here, you can see that each of the different colors is basically representing an individual galaxy. But you can see that there's a rather large scatter in these relations here, X-ray binaries and low mass X-ray binaries. So one of the things that we were interested in back here at this time was, what is leading to this scatter? Is there physically important information that drives, the variance, basically, and what can it tell us about galaxies and universe? All right, so one of the things that we've done sort of recent past is to basically statistically analyze these luminosity functions and actually are, right? And this was we would look at galaxies in the relatively nearby universe where we could resolve the stellar populations quite well. We could resolve, or we could see where the X-ray binaries were on an individual basis and measure their luminosity function. And then we were looking for a correlation. So a kind of easy thing to do is to create maps of where the star formation activity is, where the stellar mass is. And so for this example here, this is again, this is a star formation rate map. This is a stellar mass map. And then this map down here is quite important. This is called the specific star formation rate map. It's just one divided by the other. Okay, so in regions where you have very high specific star formation rate, you expect the populations to be relatively young. And so the host, or if you find X-ray binaries in that region, it stands to reason that those would be where you find high mass X-ray binaries. In the regions that are dark here, those are low specific star formation rate regions. All right, so we know from the X-ray data, where all these populations are. So this is again that X-ray image. We can look at all the point sources and map where they are. We could then divide the galaxy up, or break it down into various regions, divided by a specific star formation rate, like I was describing. So in this case, I just showed some blue in the galaxy, and you can see you have variations of populations of X-ray sources within those regions. And so this would be where, again, we maybe find high mass X-ray binaries. You can then break it up further, look at intermediate specific star formation rate, look at low specific star formation rate regions like the center of the galaxy, where most of the stars there are old. And then we're going from high mass to low mass X-ray binaries in galaxies. So we systematically then went through a sample of 38 galaxies that had very good data that allowed us to make these maps and look at the binaries on subgalactic scales. And then our goal was to characterize how how this high mass X-ray binary luminosity function scaled with star formation rate, and how the low mass X-ray binary luminosity function scaled with stellar mass, and see if we can just set of relations. Okay, so let me just show that. All right, so in this luminosity function plot, what I have is all of, you can imagine this to be, let's just focus on this one over here on the left. All of the regions of all of the galaxies in my sample that have specific star formation rate that's quite low, okay, around 10 to the minus 11.8, something like that. And I know what the star formation rates are in all of those regions, and I can sum them up to get a total star formation rate of those regions. I can measure the luminosity function of all of the X-ray binaries within those regions and construct a diagram like this. Right? As you move in this direction, you're moving towards higher specific star formation. Okay, and you can see just without very clear progression, going from low specific star formation rate, which I would say are low mass X-ray binaries, to the high specific star formation rate or high mass X-ray binary regime. Right, and so again, this is for combined, right? And so we can then model this behavior specifically by, and I'm not going to go into all the details of this, but just by saying that the luminosity, the overall luminosity function would consist of components like low mass. We know that there's going to be some background sources, background active galactic nuclei, say whether or not it's low mass or high mass. We have to do a statistical analysis here. But what we do know is that the cosmic X-ray background, its density on the sky and its number of counts or its effect on this whole picture can be pretty well the contribution from background sources. As a model for the high mass X-ray binaries, we know that they scale with star, or we're modeling them to scale with star formation rate here. And so in this type of a plot, everything's normalized by star formation rate. And so every high mass X-ray binaries, if this model holds, okay, and that's in blue. And then finally, the low mass X-ray binaries would scale with stellar mass. And since we've broken this up into specific star formation rate binning you're going to have more contribution at low specific star formation rate versus high specific star formation rate. Okay, is this making sense? Any question? Okay, so I've just conveniently drawn on the best fit of this whole procedure, but really in practice, what we do is we fit for a number of variables, this entire data set. Okay, and then we arrive at the model parameters that are here, and then the black curves in every one of these, is the prediction for the entire model. So in total, I guess this is, what is that, 7 parameters that we use to construct this model. All right, and then does a pretty good job for the average behavior that we see. So one thing we can do now with this model in hand is go back and revisit on a galaxy by galaxy basis whether or not this whole thing, the whole picture is universal. Right, so I can go back to my galaxy sample. For every galaxy, I know, I have an estimate at least of the star formation rate and stellar mass of those galaxies. I can use my model to make a direct prediction without fitting anything of what its luminosity function should be. Right. So when you do that with my model that I previously showed here, okay, my goal again is to compare with the data to see how well it does. These are the predicted luminosity functions for each of these galaxies. Okay, and then the data are in gray. Now, what I can say here, yeah.
I can comment. Shouldn't you test this with a different set of galaxies, because you are using the same test to derive the fit, and then
you can, yeah, you certainly can. One of the comments that I'll make here is, though, if you consider any one galaxy, the number of X-ray sources in that one galaxy is small. It makes a small contribution to the overall model fit. Okay, so you can have individual galaxies that are way off, and they're not going to influence the overall fit. Does that make sense? So sure, I can go to an independent galaxy and make predictions, but this is almost the same, I would say, because I have 35 galaxies. Any one is not going to drive the result. Okay, so and you can see that here. All right, so most of the galaxies, certainly on an average sense, it's going to work, and it does because by construction. But you can pick out areas where it doesn't work, right? And that is on a statistical basis. There's actually only a few that I can say are not following that model, right? And that's the ones that I've highlighted here. Okay, so we have these two galaxies, which are sort of similar in their type, and you might, I don't know if you have a good picture of what all the galaxies look like, but these would be the dwarf-like galaxies in the sample that they're very actively forming stars. Okay, but then there's also this one that doesn't fit. This is M89. This is a giant elliptical galaxy, right? And this picture doesn't fit for that galaxy. Now, in this galaxy, and then I'll focus more on what's happening in these types of galaxies. So this galaxy is a giant elliptical. One of the characteristics of large elliptical galaxies that they have very rich globular cluster populations within them. And globular cluster populations have very high densities of stars, between binary stars and other stars. And there's a lot of dynamical interactions that can take place. And it's been observed that you can drive, several of the binary stars to have tighter orbits through these dynamical interactions. And you will get more low mass X-ray binaries. One has an excess of X-ray binaries, and we know that because is due to an excess of globular clusters in that galaxy. Okay. But these galaxies, there are a couple of possibilities for what could be different about them. That they're small galaxies, so their star formation histories may be very different from the typical galaxy in the sample, and in the sense that they could have had bursty star formation histories, and the X-ray binary populations in them, which are elevated, may be due to them having maybe X-ray binaries from a younger population than your typical galaxy. That's one possibility. Another possibility is that we have investigated is that these galaxies we know are relatively low metallicity sources. And metallicity plays a role in the formation of high mass X-ray binaries, which would be dominating these galaxies, in the sense that we expect low mass X-ray low mass or low metallicity galaxies to have an excess of high mass X-ray binaries due to basically the evolution of the binary through time. I'll talk about this in a little bit more detail, but essentially, as binaries evolve, they lose a lot of mass from stellar winds. That allows them to, that causes their orbits to separate over time. It causes mass loss from the stars themselves. And so in low metallicity galaxies, you will have both less separation of the binaries. You'll also have more massive compact objects that can form as a result of the lower mass loss rates. Okay, so that could lead to more luminous sources, which we see in these galaxies. Okay, so these types of observations have led us to investigate this, these observed phenomena from a theoretical point of view. And here I'm showing, just some of the pathways that X-ray binaries go through, or where X-ray binaries are formed throughout stellar evolution. And of course, I think I've talked about these a little bit. Low mass X-ray binaries are just, a high mass star would have formed with a low mass star. That high mass star would have become a compact object at some point. And then on the time scale of the evolution of low mass star, you would turn on the X-ray binary shortly after the formation of the first compact object. So these would be 10 to 100 million year time scales where these things turn on. About 10 years ago, again, we started with a generation of population synthesis, and those were designed to predict the X-ray power output of a population of sources as a function of age. Okay, so I'm showing here just one particular model from Fragos et al. 2013, where that was just based on the population synthesis evolution expect for the formation of many binaries with roughly solar metallicity or so. Shortly after the star forming event, the high mass X-ray binaries will turn on, and then their contribution dies off on hundreds to billion year time scales when the low mass X-ray they start to decline as the donor star mass moves to lower and lower mass stars. Now we think then that this picture is, as I described before, dependent on metallicity. So at about a 10th solar metallicity, we're expecting this to be elevated, this type of evolution to be elevated by a factor of 10 or so, in particular for the high mass X-ray binaries, with potentially less difference there for low mass X-ray binary sources. All right, so this picture tells us then that the X-ray binary would be sensitive to metallicity, as I was describing. To gain sort of a more I should say quantitative prediction for what these theoretical models would do or would predict for local galaxies. At the time, what we would do is take these tracks of X-ray power output as a function of age, and then fold them into how the properties of the universe have changed over cosmic time. Okay, if you think about it, any one galaxy that you look at has all this baggage of history throughout time. And what you see in that galaxy is going to depend on the history of when stars formed and what their metallicities were, for example. All right, so to get at sort of a average sense of what the universe's scaling relations would be like from population synthesis point of view, you would take these tracks, fold them in with how, say, the star formation rate density of the universe changed over time, how the stellar mass changed over time, and then how the average metallicity of within galaxies changed throughout the history of the universe. And I'm drawing it this way. This is that's a function of redshift. So early universe over here going now to the present day. In these units, this would be at 1 here. All right, and so you know, we would take population synthesis models, fold them through those you know, tracks, and then you would get also back, you know, how these scaling relations would evolve with time. So this is now showing the low mass X-ray binary per stellar mass as a function of redshift, and then high mass X-ray binaries per star formation rate as a function of redshift. For various models. Okay, in total, we did 288 different scenarios, varying some of the physical prescriptions for how you know, evolve binaries, the distribution of you know, mass ratios, separations, things like that. And so then ultimately, excuse me, ultimately then, you arrive at redshift 0 with predictions on these scaling relations that we were observing in the local universe. Okay, and then what you can do, and these are the scaling relations again, is you can match the best theoretical models to the local scaling relation values to get at a sort of best population synthesis model that we have here. And just to show, you know, this would constrain some of the parameters of the physical models that are in here. I'm not going to go through these in detail, but some of the things that are varied are things like wind prescriptions, common envelope prescriptions, again, mass ratio distributions, supernova kicks, various things in here. Okay. But not only do you get a sort of preferred model for what's happening at redshift 0, you can see that you get these tracks excuse me, for the evolution of these scaling relations throughout the history of the universe. So one thing that our group was interested in was to test, you know, these tracks, or to, you know, empirically derive how the scaling relations themselves would evolve throughout cosmic time. Okay. And again, what we were expecting is that as you go back to the high redshift universe, these scaling relations for low mass X-ray binaries might increase because the average age or the donor stars here for the low mass X-ray binary population would be younger, more massive stars, so higher mass transfer rates, and so more power output per stellar mass as you go back in time. For the high mass X-ray binaries, the prediction was that you have this elevation as you go back to high redshift because you're looking to populations where the metallicities of the galaxies are lower. And as I described, you'd expect that to produce more luminous high mass X-ray binaries for a given star formation. Okay, so to do this empirically, we would use the deep observations from the Chandra deep fields. Here I'm showing the overall Chandra deep field south, which is a 7 million second exposure on a patch of sky that doesn't have anything particularly interesting about it, except galactic absorption, for instance. This also ends up being, of course, the regions where other multi-wavelength data sets have invested, or a lot of other observatories have invested a lot of time. So, for example, the Hubble ultra deep field is here in this small window that you can see there. Of course, within the Hubble ultra deep field, there's loads of galaxies, thousands of galaxies in this small region. But then you look at the X-ray region, and it's not as impressive in terms of population density. Okay, so here's that same region now with the 7 megasecond Chandra deep field south. You know, we're detecting tens of galaxies in this region. Across the entire field, we detect a few hundred sources that we think are galaxies. The majority of the X-ray sources in this field are active galactic nuclei. Okay, so these aren't even related. And so we've had to, develop other techniques to study sort of the average galaxy scaling relations as a function of redshift to do that. And so for the most part, then we've been using X-ray stacking analyses where, we can isolate the positions of the sources where we know the properties of those sources. And then we can go to the positions of the sources within the X-ray image, and then extract out the X-ray information locally. And so when this works well, you will have, say, a population of galaxies that you select. Say you can grab a bunch of galaxy star formation rate, for instance, and then you go to the X-ray data and you look at them. Not a lot of interesting information on any individual galaxy. But then you sum them all up, and the stacked image gives you an average signal of that population. And so you can calculate things like, that particular grouping of galaxies. Now, this can be extremely powerful for a data set like this. We have 7 million seconds of Chandra data. It's not uncommon, but sometimes we will have something like 500 galaxies that you can just go and group and stack all together. And then your average signal would be as if you looked at that one galaxy for 110 years with Chandra, just continuously staring. So it can be a pretty massive leverage of the data that we have in these fields. Okay, so what we've done then is we've divided galaxies into redshift bins. And then within any given redshift bin, we've looked at how the X-ray power output scales with star formation rate and stellar mass. And so, what we're interested in is looking at how the scaling relations themselves. So again, up here, high mass X-ray binaries with star redshift. And so here are the measurements that we've made using this technique. And indeed, what we do see is some increase in the high mass X-ray binary scalings with redshift, and then also potentially an even more dramatic increase with locally expected. But then when we directly compare these with sort of the best population synthesis models, best in terms of how well do we describe this data, it actually looks pretty nice. Much nicer than I would have expected. So just to emphasize what's happening here, these red from these population synthesis models, there's no degrees of freedom aside from selecting the best of the 288 here. I'm not able to shift these arbitrarily with respect to the data in any way. And so, for me, at least I thought this was a pretty outstanding result relations. And again, the behavior of or the influence of star formation history and metallicity is sort of on this empirical diagram now. But what we wanted to do, we have the redshift evolution here of showing us the formation of X-ray binaries. We wanted to go back and revisit local galaxies where we can actually look at luminosity functions and then see the impact of metallicity and star formation history on those sources or on those galaxies. More direct because we have much better data. As I was saying, we had to do all this stacking analysis here. It'd be nice to see this impact on galaxies where we have good data. Okay, but before I get there, I wanted to emphasize that a lot of interesting stuff came out of this result. So this is showing now the power output of the universe now per unit volume of the universe due to various X-ray emitting source types as a function of redshift. So we know, in the deep fields, most of what we detect are AGN. So of course, you'd expect those to be the most powerful things in the universe in X-rays. And indeed, we see that the X-ray emissivity of AGN in the universe has been large, at least out to redshift of 5 or so. But the prediction going out to higher redshifts is that this AGN influence might drop. This is a matter of a lot of debate, actually. At least how it drops is a matter of debate. But as you go back to really low metallicity sources, what we predict is that high mass X-ray binaries will eventually exceed AGN in terms of dominating the power output of the universe at very high redshift, which is a very interesting result. Another thing that happens is that if you have low metallicity, if you basically have just low metallicity, the effects of X-ray absorption as the X-rays try and make their way out of the galaxies reduces. Okay, so in a typical galaxy, you have a lot of absorption at low energies. Low X-ray energies means like very high UV energies. Okay, so this is the extreme UV. So the X-ray emission gets absorbed in the interstellar medium of a given galaxy. But if your metallicity is low, for a given column density, you end up increasing the amount of power output from those low energy photons that escape the galaxy into the universe. And so this diagram here is showing the effects of its 8 or 10 maybe universe, where your typical absorption might look something like this black line, or sorry, this red line. And then when you take into account the change in metallicity, you actually get a lot more power output coming from these low energy photons getting out into the universe. And then the intrinsic spectrum is this green thing here. So the impact of that is that you can get low energy photons in terms of X-rays, but high energy photons in terms of ionization and hydrogen. And then those photons can get out into the intergalactic medium, and then as they interact with on larger, relatively large or long path lengths, they can ionize the intergalactic medium at some level, not in the sense of reionization, but those high energy photons, as they interact with hydrogen, and ultimately cause. So in terms of your temperature relative to, say, the CMB out at redshift of 15, the absorption effects matter in terms of what the certain temperature of the intergalactic medium would be. So this would be if you had standard absorption, having that lower absorption due to not having so many metals. Right. So this was another very interesting avenue that came out of this. You also have more energy emissions from X-ray binaries to consider there too. All right, another area that was quite interesting is that it's been observed that in low metal high ionization species that are observed in star-forming galaxies. For example, helium-2 here is a feature where people have tried without a lot of success to model, the stellar populations and reproduce. However, if you start to account for the potential of X-ray binaries to produce a lot of intrinsic, EUV radiation, you can, given prescriptions that are consistent with scaling relations, you explain the intensity of these ionization lines. And so the typical picture is something like this, where this is an SED showing stars in gray, and then these various lines here are showing different models for potentially producing a lot of extreme ultraviolet radiation that can, ionize helium-2, which is photons basically above this line here. All right, and more directly, people have observed helium-2 nebulae around ultraluminous X-ray sources. Again, kind of, giving credence to a source of ionization for these low metallicity galaxies. 10 minutes. Okay. All right. Thanks. Okay. So what I was saying before is we wanted to observe the effects of metallicity and star formation history more directly. in galaxy populations. So one of the things we did is, we had this, as I was showing before, we had the sample of 38 galaxies where we could resolve the populations into individual sources, study luminosity functions, etc. We gathered a similar data set where we had focused on galaxies with very high specific star formation rates, so dominated by high mass X-ray binaries, but then included only galaxies where we had fairly good gas phase metallicity measurements that spanned a broad range of metallicities. And then we study their X-ray binary populations. Right. So here I'm just showing the basic results of this. Right. So these are luminosity functions of that sample normalized by star formation rate, but then in progressively lower and lower metallicity bins of the galaxy sample. And so what we can see then is that the high mass X-ray binary luminosity function at relatively high metallicity goes from something that's kind of like a power law, maybe even a break in the power law right here, to having more and more luminous larger numbers of ultraluminous X-ray sources per unit star formation rate as we go to lower and lower metallicity. The low luminosity source population itself doesn't seem to change a whole lot. It seems to be that metallicity is driving changes in the ultraluminous X-ray source population. This is a result also, observed by Konstantinos as well. And so, anyway, so it's one of the things I know is that this is very difficult to find galaxies of very low metallicity. We tend to be kind of limited by dwarf galaxies that are at low metallicity that don't have rich populations of X-ray binaries as it is. So we have to gather lots and lots of galaxies to do that. But in any case, we have now then what is sometimes called the fundamental plane of X-ray emission from binaries, where the power output per star formation rate of the high mass X-ray binaries seems to decline as a function of metallicity. And so this model for that in the local universe, and then the population synthesis model is shown here in this magenta dash curve. And we are seeing some clear differences between what's being predicted by population synthesis models and what we're observing. And one of the things that I'm doing here, develop population synthesis models that make this particular type of prediction in a much more improved way than we did about 10 years ago. Okay, so if you look then to the equivalent, say, redshift or the equivalent metallicity, our average metallicity for what this would be a redshift 0. This is sort of our average metallicity. And as you go to higher and higher redshifts, you're looking at more luminous populations per star formation rate. Something that we observed directly with the deep field. So this is all actually kind of holding up nicely there. Another fact that in low metallicity galaxies, absorption, intrinsic absorption could be different. So we've been looking at spectral properties of galaxies as a function of metallicity, spanning 0.3 keV all the way out to about 30 keV. These are kind of hard data to gather. We use a combination of XNM and Chandra and a NuSTAR to span this full range. But we are seeing these basic trends, so that the yellow and reddish samples are kind of more solar-like spectral energy distributions. And then as you go to lower metallicities, we have the green, and then even lower the blue curves that are in there. And we see both, the increase of the X-ray binary population, but also less intrinsic absorption of the spectral energy distributions there. And this has then allowed us to build this kind of toy model of what the spectra of galaxies are, which is in action here, but you can see the metallicity of any given frame here shown up in the upper right. So we go from solar over to lower metallicity, less absorption you see coming up over here, and then just an overall increase because of the population becoming more luminous there. So we're starting to build up these more informed models of the galaxy spectra as a function of these properties as well. For star formation history, we've started to investigate the effects of star formation history on the X-ray binary population in a more direct way. So our technique here is to use multi-wavelength data analysis to basically back out the star formation history of any galaxy. And in our case, we've developed this code called Lightning, which is an SED fitting code. At its heart, you have, as many other SED fitting codes have, the stellar populations at various ages. Okay, so in this diagram, you can think of these as, if you have a population of 0 to 10 million years constantly forming stars at the same rate over that period of time, you would produce a spectral energy distribution like this purple one. This one would be if you had a period of star formation 3.2 to 10 billion years ago at a constant rate, you'd then at the other extreme form this or have a contribution from this set of stars. So in our modeling of observed SED, right, we have the stellar populations, we have absorption, and we also have dust emission in our models. I can't go into all the detail here. But you're looking for linear combinations of these different base sets to tell you to describe this SED, and then ultimately what you back out then is the star formation history of the galaxy. So in this case of the data set, this data set that I show here, we fit this with our models, and we're able to back out sort of the star formation rate as a function of time for that one galaxy. Right now, I've said this is a deep field region. Okay, so again, our X-ray data are not able to look at a lot of detail of any individual galaxy, but we can do a statistical analysis of the full population of galaxies by considering a model where we say that the total X-ray power output of that galaxy is related to some scaling X-ray power output per stellar mass of a given age bin, and then summing up all of the different the masses of the populations of each age bin times the scaling relation. That gives you a model for the total predicted power output. Okay, so in any one galaxy, as I say, we don't have great data that we can say, all right, this is necessarily even detected, but if we take as a full population, if we had 350 galaxies where we had a lot of the star formation, where we had the star formation history information, we can fit a model that will tell us the scaling Lx over stellar mass as a function of age on average for that entire population of galaxies. All right, sorry, I know this may not make complete sense given my explanation here, but I'm happy to talk about that in more detail with anybody if you're interested. But the bottom line is that you pull out the scaling or the evolution of X-ray emission per unit mass as a function of age directly from this analysis in an empirical way. Semi-empirical way from my grad student Willie Gilbertson showing this progression of X-ray power output as a function of age. And then again, we can compare these with older population synthesis models to see how they stack up. And we do see important differences in some of the predictions that come from this model. Then is apply these types of techniques to local galaxies. Look at how luminosity functions vary as a function of age, but then also investigate how metallicity plays a role as well. Okay. So I will okay. So I'll try and wrap up here in a minute and just tell you some of the things that we're currently working on as an extension of this work. Okay. So again, I just mentioned this. We were characterizing X-ray binary populations as a function of star formation history and metallicity. We've done a little bit of it in local galaxy populations and basically connect the entire universe. Okay. Another thing is, getting to the precision of our star formation histories is not high. We're not, able to, look at smaller time scales scales with the type of analysis that galaxy populations that we're studying, where you can look at, for example, color magnitude diagrams to get very detailed star formation histories on short time scales. And in those cases, we expect there to be a lot of changes in, say, the high mass X-ray binary populations. Right after a star formation event, you should have no high mass X-ray binaries. You need some time to form those compact objects. So after about 5 million years, these binaries should ramp up, and then they should evolve rather quickly on 10 million year timescales. Really, the timescales we can't probe yet with the analysis we've done. We also are working on population synthesis models. One of the main reasons I'm here is working with Konstantinos on some of the more recent population synthesis models, in particular the Poseidon code. Ultimately, it would be great to connect some of the constraints we have on X-ray binaries along with gravitational wave source statistics, and have a fuller picture that's self-consistent with observations. This is a large goal, okay, but we're sort of looking in that direction. And then we're continuing to develop this SED fitting code that I was describing before. Most of what it has been doing so far has been modeling the ultraviolet stellar data all the way out to the far infrared. Eventually, we hope to include X-ray binary populations, hot gas as well, to make simultaneous X-ray predictions with this code. And then one of the sort of more future things that I am interested in is how we can look at X-ray luminosity functions as a function of the various types of objects, different types of compact objects and different accretor types. There are methods using, say, for example, NuSTAR, where we can differentiate between black holes and neutron stars and galaxies. And then we can also, for relatively local galaxies, find direct counterparts to the sources, find what the nature of the donor star is. And then we can, further break down the data into more degrees of freedom that we can use when we try and describe these populations. All right, so I should leave it here in hopes that I'll get some questions.
Thank you, Bret. So are there any questions in the audience? Yeah.
Thank you very much. It was very nice. I have a question concerning something that you mentioned. Last slide, but namely, namely the possibility of using gravitational wave statistics to illustrate the gas population of high mass X-ray binaries. I want to ask if do you think this is possible with the data that we have to generation interferometers in the next round, like 4 or 5?
Yeah.
Or do you think that we will need the third generation interferometer to have a value?
Oh no, I mean it helps a lot more.
Sorry, can you?
Oh yeah, sorry. Okay, the question. The question was, I had mentioned that one of our long-term goals is to combine X-ray binaries and gravitational wave source statistics, to help constrain some of the theoretical models here. Is that possible now? Or do we need to wait for future generations of gravitational wave experiments to do that? Well, the short answer is it's definitely possible now. People are at the moment, unfortunately, people take sort of an either or direction in terms of modeling these populations and don't do them all together. I think, and I understand it's very difficult to do everything together because, gravitational wave sources themselves can be modeled without having to include all of the X-ray binary details. Okay, you don't need to understand how mass transfer onto a compact object produces light. That's not necessary. You just need mass transfer histories. And so people tend to actually already use gravitational wave frequencies to constrain these models. So yes, it's possible. I can't tell you because nobody's done the full-on explain everything self-consistently, see what you get. I can't tell you what kind of improvements you would get from future generations of of these gravitational wave experiments, but it's always it's always nice to have this. Yeah.
Yes. Any other quick question? No, can we check in Zoom if there is any opportunity to talk there? We need to be back there.
There we go. Okay,
So,
we cannot hear anything. Well, that was, I think we took care of that.
yeah.
Are there any questions on Zoom?
Okay, it seems
Okay.
there is not. So, thank you again, Bret, and let's go. All the rest of the next week and day. So you have extra discussion, want to do questions or whatever, please find me in the third floor in the visitors room or me. And,
Yeah, I'd love to chat.
yeah.
Next week.
Yeah. Yeah.
Yeah, in and out, but yeah.
Yeah.